Thank you very much for this kind invitation. I'm very happy to give this seminar today. I'm going to talk about modeling and controlling turbulent flows through deep learning, and my work is at Flow within KTH, Royal Institute of Technology, and is funded among others. The funding is mostly from the European Research Council, ERC, and other foundations as well. So I'm going to start, and now you can see my next slide, right? Yeah, so I'm going to start by giving a short introduction about machine learning and some of the success stories that it has witnessed in many areas. You can see, for example, the case of image classification, where machine learning has been really good at being able to identify features in images and obtain better features and better performance even than humans at this task. There are many other tasks where machine learning has actually succeeded. And perhaps one interesting case, one interesting example is when in 1997, the world champion of chess, Garry Kasparov, was defeated by the IBM Deep Blue machine. This was something that was at the time a big achievement for machine learning or algorithms in general. It really got a lot of media attention, and Kasparov didn't take it so well, actually. And it turns out that chess is a very easy game for machine learning. So using games to be able to tackle the possibilities and the resources of machine learning is a quite common task, because games present challenges that can be quite relevant in a narrow area, but progressively wider and wider. And chess is actually well, given the number of moves and the number of turns that you have in a typical chess game, it turns out that almost by brute force computing, you can play chess pretty well. However, if we think of the game of Go, which has become quite popular recently, because of the developments in machine learning, it turns out that it's much more difficult to play Go. And you can assess this in terms of the number of moves that a typical turn has and the number of turns that a typical game entails. So one can raise the number of moves to the power of the number of turns. And it turns out that Go is many orders of magnitude more complex than chess. So to play Go is not enough with just having a sort of brute force computing, evaluating all the possible options and going forward. Here, the algorithm needs to develop a certain sort of intuition, to be able to perform in this task. And this game has become very popular because of the AlphaGo team, the Google DeepMind team, who published in Nature how using the data of the games of the best human players, they could train an algorithm, AlphaGo, that could actually defeat the world champion of Go, as you can see in this picture, by 4-1. So Lee Sedol, who was the world champion, was defeated by this algorithm that was learning just watching the best human players. And this was really a great achievement, because this was expected that it would happen in many decades, and actually it happened 6 years ago. So it was already quite remarkable. But perhaps even more remarkable would be the work by the same team, also in Nature, published 1 year later, where they developed the algorithm AlphaGo 0. And in AlphaGo 0, the interesting thing is that they did not show any human game to the algorithm. They used something called reinforcement learning, in which the algorithm learned by playing against itself. So it was just given the rules of the game, and playing against itself, it could progressively improve. Here in this vertical axis, we can see the performance at the game of Go. And here in the horizontal axis is the hours of training. And this horizontal line would be the best human performance. So the AlphaGo that defeated Lee Sedol. And we can see that in less than 2 days of playing by itself, this algorithm reached superhuman performance. So one could actually defeat the best human players ever, just with less than 2 days of playing by itself. So this, of course, is a very narrow task, or a relatively narrow task, but it kind of shows that there is some potential to use machine learning in complex problems and in high-dimensional problems with many possibilities. This really motivates the work that we had recently in Nature Communications. You can see the reference here, where what we did was to assess the impact of artificial intelligence on the 169 targets of the United Nations. So this is the sustainability agenda for 2030, where we can see that 79% of all the targets could be positively affected by AI, which really shows a quite positive potential, although 35% of them can be inhibited by the development of AI. So one has to also be aware of the limitations and the possible challenges. But in general, there is very big potential in a very wide range of areas, because these SDGs, these Sustainable Development Goals, span a quite broad range of disciplines. We also published recently in Nature Machine Intelligence, where we argue that it's important to open the black box. So it's important to develop deep learning models that are interpretable, so that one can actually have a chance to harness all the potential, no? All the potential that we have for all the Sustainable Development Goals, image processing, and so on. Can only be fully exploited if we have the right framework for interpretability, if we know how these algorithms are actually making the decisions that they are making. And perhaps looking a bit more into fluid mechanics, which is the topic that is going to be covered today, what we know is that machine learning has been applied in a very wide range of areas. 20 years ago, there was the work by Milano and Komosakos, where they modeled the near wall region of a channel with neural networks. That was quite some pioneering work on neural networks and fluid mechanics. There has been some more recent work on subgrid scale modeling for LES, also on the generation of inflow conditions. Machine learning applications to RANS modeling, and perhaps an interesting area, which is flow control, as in the work by Branter and others, and the potential that one can have with physics-informed neural networks for sensing, no? How one can actually improve medical tests through these PINs, these physics-informed neural networks, that I will be discussing with more detail later in this seminar. So the first problem that we're going to look at is what we call non-intrusive sensing. So non-intrusive sensing is based on measuring, for example, at the wall. We have a turbulent flow, we measure at the wall, and we want to predict what the flow is doing above the wall, at different distances above the wall. And why is that important? This is important because if we measure at the wall, we're not disrupting the flow, so we are not perturbing the characteristics of the flow. And this is a very interesting application for reactive control. So if we know what the flow is doing above the wall, we can design better controls so that we can actually tackle certain structures and certain scales in order to minimize the drag, for example, no? Of a certain application. So essentially what we will do is that we will predict, based on this blue plane, which is the wall, the characteristics of the flow in this yellow plane, which would be an off-wall location for these fluctuations. And to do this, what we did was to use DNNs, direct numerical simulation, to produce a very big database of an open channel flow. This is a turbulent open channel flow. The reason why we did an open channel and not a regular channel is that the dynamics of the large scales is simpler in an open channel flow. And then basically what we did was to produce all this DNS data, all this direct numerical simulation data, so that we can do a supervised training approach in this first problem, and we can map the information at the wall with what happens above the wall. To do this, one can apply different types of deep learning methods. One possible method is what we call fully connected layers, fully connected networks. This is the example that we are seeing here. And the problem of these networks for this type of application is that because all the neurons are connected in one layer are connected to all the neurons in the next one, this is not very practical for image processing. Because in the end, this leads to very large numbers of parameters, and there is no information about the spatial distribution of the inputs in this type of network. However, there's another type of network, what we call the convolutional neural networks, that you can see on the bottom, which are very widely used for computer vision. So in these networks, I have an input, which will be displayed over here. Have a little window, what we call the kernel of a certain filter, And this little window, what it does is that it's sweeping through the input with a certain stride, and it's applying convolution operations to obtain the feature maps, which are the outputs. So in this particular example, the filter has a size of 3 times 3, which means that each output in the feature map receives information from 9 inputs in this input image. So now we will, because turbulence has a certain structure, so turbulence is characterized by coherent structures with certain correlations in space, then using computer vision tools, for example, CNNs, convolutional neural networks, is going to be a suitable approach to be able to exploit these correlations and to improve our predictions. So going back to this slide, what we will do is that we will use information at the wall to predict the flow above the wall at different distances. So at the wall, what we can do is that we can measure the 2 wall shear stress components and the wall pressure. We can measure that more or less easily. And we're going to predict the 3 velocity fluctuations at different distances from the wall. So the stringwise, wall normal, and spanwise fluctuations at different off-wall locations. Okay. And again, the application for this will be closed loop control, which I will also discuss at the end of this seminar today. So this is a schematic representation of my CNN, my convolutional neural network. What I have is an input with 3 channels, and the 3 channels are the 2 wall shear stress components and the wall pressure. I have an output with 3 channels, which are the 3 velocity fluctuations at the target location. And I have a total of 6 hidden layers, as you can see here. This is an architecture that we chose initially. Now we have refined a bit more this architecture, but this actually turned out to work pretty well, in fact. The numbers that you see here are the number of feature maps that we obtain for each of the hidden layers. And as you can see, in the first layer, we have a filter with a depth of 3, because we have 3 outputs, and the kernel has a size of 5 times 5, which means that we have 75 parameters. This is for the first of the filters, and we apply a total of 64 filters in the first layer. So each filter has 75 parameters, and we will apply a total of 64 filters, which will give us a total of 64 feature maps. Okay, important. Each filter identifies one or several features. So this is something important to understand in how these convolutional neural networks are actually operating. Before going a bit to the next slide, what I want to also mention is that because of how CNNs are built, the first layers will focus on features that are more abstract and simpler. So those features can be segments, can be lines, can be circles, regions of recirculation. And as you are getting closer to the output layers, so as you're going deeper into the network, this concatenated sequence of convolutions is building a more and more complicated set of features. So one can actually build progressively more complex structures by building from the simpler features that are identified in the first layers. Okay, so this is how CNNs actually work. So this is a summary of the setup, the 3 inputs on the left, the 3 outputs on the right at different locations. This is the CNN. And all of this is actually documented in this work by Guastonia and others in JFM, in the Journal of Fluid Mechanics. So this is published from last year, where you can see all the details of the architecture. Today, I will be highlighting some of the most important features of this model that we are developing. Now, what I have shown you so far is what we call a fully convolutional network. Okay, so we take the input, which is a plane, just an image at the wall, and we take an output, which is another image. It's a peak-to-peak prediction. So we have an image input and an image output. And through a sequence of convolutions, it's a fully convolutional network, then I obtain my output. However, there might be another alternative approach, which I introduce here. This is what we call the FCN-POD, so fully convolutional network combined with POD, where POD is proper orthogonal decomposition. For the ones who are not familiar with POD, it's essentially PCA. So principal component analysis applied to fluid mechanics is basically POD. And it's basically a linear model decomposition, so a dimensionality reduction approach. What we do is that we will basically perform POD on each of these subdomains, and instead of predicting the full signal, what we do is that we will predict just the temporal coefficients. So the spatial information is encapsulated into these spatial modes, and we will only be predicting the temporal coefficients instead of just the full signal. And all the details of this method can be found in these two papers, so in the JFM and also in physics of fluids. So we will look at the FCN method, just convolutions, and the FCN-POD, which also includes the POD part of it. Now, let me show you the results at friction Reynolds number 550. So Arita 550, that's a reasonably high Reynolds number, not very high, but it's already turbulent, and it exhibits separation of scales, which is quite good. And what I'm showing you is the instantaneous streamwise velocity fluctuations. So the first column is y plus 15, so that's a plane that is quite close to the wall. And the second column is y plus 100, which is a plane that is far away from the wall. The reference is the third row, which is the DNNs. So the DNNs data is the reference, the baseline, the ground truth, and then we're going to show you different predictions. The first row is a prediction based on what is called the extended POD. The extended POD is formally equivalent to linear stochastic estimation, and it's basically a linear method. So we are relating the input at the wall with the output away from the wall with a linear method. And of course, we know that turbulence is non-linear. So obviously, this method is going to exhibit some limitations. And what we can see by comparing with the third row is that the predictions are attenuated, so there is less fluctuation intensity, and they are smoothed, they're filtered. So some of the small scale details which are associated with the modulation, the nonlinear modulation, they're actually lost when using the extended POD as a prediction method. The fourth row shows the FCN, which is the fully convolutional network. And what we can see is that at y plus 15, we get an almost perfect prediction. So the flow close to the wall, we can predict it almost exactly by using the FCN approach. And if we look at the plane at y plus 100, so far away from the wall, what we see is that it's actually the FCN-POD, so this method over here, that shows the best agreement with the reference. If you think about it, and what we see is, of course, some attenuation and some of the details are lost, but the most important scales, all the relevant structures are actually there, are actually here. So with the FCN-POD, we can actually get very good predictions. And if you think about it, what happens with the POD is that it's a very efficient way of encapsulating the information into spatial modes. And if you are far away from the wall, in principle, you have fewer large scales, which can be more efficiently encapsulated into POD modes, and then predicting the temporal dynamics of those modes is going to be more efficient than just trying to predict the whole plane. But close to the wall, because you have a lot of detached structures and a lot of information that is not so coherent into larger lumps of data, then the POD is not so effective. So the POD doesn't work as well close to the wall as it works far away from it. Okay. So what I'm showing here is the statistics, so the RMSs, the velocity fluctuations in the stringwise, wall normal, and span-wise directions, where the horizontal axis is the wall normal location in plus units, and the vertical axis is the fluctuations also in plus units. And the triangles are the FCN predictions, the blue dots are the FCN-POD, and the green rectangles are the linear method, the extended POD. So what we can say is that, of course, all the predictions get worse as we get farther away from the wall, because the data is less correlated, the wall with the output data. And we see how the FCN performs extremely well in the near wall region of U prime, so we can predict the peak extremely well. And if we move farther away from the wall, we see how progressively the FCN-POD becomes better. So at some point, these large scales are very well encapsulated by the POD, and therefore we can get better predictions. What is interesting is that the FCN at y plus 15 has an error lower than 1%. So this is what I was mentioning, that we can predict the flow close to the wall extremely well. And usually when you do control, at least at low Reynolds numbers, that's the type of plane that is most interesting for you. Farther away from the wall, we can actually get errors of around 25%, which is still quite reasonable in terms of locating those large scales that you want to maybe target for your control. One important application of this is what we call transfer learning. So in transfer learning, what we want to do is that the information that has been learned in one case, we can reuse it in another case, which is similar enough to the first one, but a bit different as well. So we can actually transfer some of that knowledge. And one first example of transfer learning that we can show is when we want to use the information learned to predict at y plus 15 to predict also at y plus 50, so far away from the wall. This is at Reynolds tau 180. And what we did was to freeze the 3 first layers and only retrain the 3 last layers. And the hypothesis behind that is that the first layers are capturing or are reacting to features that are smaller and more abstract. And those are in principle more similar in the 2 locations. Whereas far away from the wall, what we're looking at is larger structures. No? So those are maybe more dependent on the location where you are at. So by doing transfer learning like this, what we obtain are essentially the same results in terms of accuracy, but we are able to reduce the amount of training by a factor of 4. So we can significantly reduce the training time by effectively exploiting the possibilities with transfer learning. And another application, which I believe is quite interesting, is to use what we learn at Reynolds tau 180 for predictions at RE tau 550. So what we did in this case was to train a network to predict at RE tau 180. And then the training at RE tau 550 is initialized from the weights that we had at RE tau 180, right? So we don't start from random values, we start from the same weights. And what we can also show is that we can reduce the amount of training data to 25% of the original. So again, we reduce by a factor of 4 the amount of training data by using transfer learning. And what is interesting is that this simulation at 550 is many, many times more expensive than the simulation at 180. So this is a quite smart way to train networks. If you are you can use very cheap data to do most of the training and then do transfer learning, so that we can actually minimize the usage of very expensive data to finalize the training. And then we can train a network that works at 550, but most of the training was done on 180, which is much, much cheaper from the perspective of data generation. Okay. Now, so far, everything that I have shown you has relied on the assumption that we have all the information at the wall. So if you look at the wall, if you look at it, I have a very finely resolved input at the wall. But in reality, things are not like that. In experiments, you don't have so much information at the wall. You only have few measurements, few sensors. And that's what we want to model in this next part of the presentation. So what we're going to do is assume that at the wall, we only have few sparse measurements. And from those, I'm going to reconstruct the information at the wall with very high detail. And with that information, I will predict the flow above the wall. To do that, I'm going to use a very popular architecture that is used for super resolution, and is GANs, generative adversarial networks. So this type of architecture, which you can see here for super resolution, works as follows. We start with this architecture is divided in 2 parts. It has a generator and a discriminator. So those are the 2 parts of this network. The generator has the task of producing from low resolution images, high resolution images, following the statistical properties of the reference data. This is a supervised approach. And the discriminator, what it has to do is differentiate which high resolution images are real and which ones have been produced by the generator. These 2 parts of the network, they're trained together, using game theory, and they have, of course, antagonic roles, right? So one is against the other one. That's why they are adversarial. The idea is that they both get better progressively at their own tasks. So the generator can eventually produce very, very realistic images that can fool the discriminator and fulfill the statistical properties of the reference data. The architecture that we will use is this one, and it has two steps. So in step number one, we are producing high resolution images at the wall from the low resolution input. And in the second one, that high resolution input will be obtained to produce velocity fluctuations above the wall. Okay? So that will be basically the idea. And what we will show now at the bottom is if we start from this is the instantaneous wall shear stress in the stringwise direction. If we have the DNS, which is the reference, we can downsample, so reduce the resolution by a factor of 4, 8, or 16 in each direction. And from this input, I can try to reconstruct the prediction, the output, and here are the predictions that we get. So of course, the more downsampling, the more attenuation of the fluctuations. That's natural because I have less data to start with. But what is quite interesting, if we look at this case, where this input is basically telling me very little about the DNS, what we do is that we can reconstruct the location and the size of the structures extremely well. So from something that is basically a mess that doesn't tell me so much, I can actually reconstruct very well the location and the sizes of the structures. I can also find that these structures look very physical. I have the typical streaks in the near wall region, and that these predictions are in principle quite reasonable and can be used for flow control. So all the details of this work, super resolution in turbulence, can be found in this article by Vinuesa and others in physics of fluids. Okay. So if we want to use now the coarse input to make predictions far away from the wall, what we can do is to have a look at this representation. In the first row, we have the DNS, which is the reference data. The columns are y plus 15, 30, 50, and 100. So I'm going farther away from the wall. And the rows denote additional downsampling. No? So this is 4, 8, and 16 factor of downsampling at the wall. So of course, this is the easiest prediction because I have very low downsampling and it's very close to the wall, and the prediction is in excellent agreement with reference. And this one over here is the hardest prediction because I am very far away from the wall with very high downsampling. So even in this case, we're comparing this panel with this one. So even in this case, what we can do is that we can identify the streaks. We can identify the large-scale streaks in the outer region. We know where they are and we know their physics. Of course, we are missing a lot of the nonlinear details and the modulation, but if we are targeting to control these large-scale features, we can actually do it. So that's actually quite a remarkable and interesting result. Okay, so that was all about predictions from the wall to above the wall. And this is, has a clear application for reactive control and non-intrusive sensing. Okay. Now, the next application is going to be the other way around. So we're going to try to use information from far away from the wall to predict the flow close to the wall. And the idea behind this is that we can use this hopefully for wall models, no? For off-wall boundary conditions. So if we can predict a reasonable boundary condition close to the wall, then we don't have to simulate everything in very high level of detail, and therefore we can get reasonable predictions there for wall models, essentially. So we are using fully convolutional networks. Here I'm showing the error as a function of delta y plus, where delta y plus is the distance between input and output. So the input is far away from the wall, and the output is when it gets closer to the wall. That means that delta y is increasing. So for larger delta y, I'm closer to the wall, and of course the errors increase because the data is less correlated. That makes sense. What we also realize is that these predictions are challenging, more challenging than the ones before, for two reasons. When you're predicting from the wall to above the wall, the wall already has the imprint of those large scales through modulation and superposition, whereas the other way around, those large scales don't have the imprint of the scales that want to be predicted. So that's one limitation. We have missing scales to make the prediction. And the second point is that we are using a very large scale as an input, and our receptive field of the CNN is only one part of that very large scale. So one needs to do something to improve the architecture in order to efficiently exploit the data that we have as input. This is something that some time ago was done by Mizuno and Jimenez, where they used rescaling of the input plane to put it in the output. What we wanted to do was to try to do it with CNNs, with convolutional neural networks. And what we are showing here is that the input is at y plus 100, so that's the input data, and the output is at y plus 50, so that's what we have. And what I'm showing you here, the columns are the U, V, and W, so the velocity fluctuations in the three directions, and the rows, the first one is the reference input, so y plus 100. The second row is the target, which would be the DNS at y plus 50. And the third row would be the prediction. So basically, I want to compare the third row with the second one, which is the ground truth, this type of prediction. And what we can see for U, V, and W is that the predictions look very reasonable, actually. So I can actually get results resembling very much the structure of the flow, the patterns, the different scales. All this information, by the way, can be found in this article in arXiv. So if you're interested, you can actually get it here. But what we can see is that even if the predictions are pretty good, we still have around 20% error, 19% in fact. So we have good accuracy, but probably not enough to run it as a boundary condition. So that's something that we are also looking at to try to improve. If you look at the spectra that you can see here, this is the stringwise, wall normal, and spanwise power spectral densities. And these are the two-dimensional spectra at y plus 50. What we see essentially is that the energetic peaks are there, but the orange lines, which are the predictions, miss most of the small scales, which we knew about. That was not anything new. And there is a certain displacement of the peaks. So these are somehow things that maybe we can fix with max pooling to better identify the input features, and maybe with GANs to be able to reconstruct the scales that we are missing for the small scale part of the spectrum, essentially. Okay. So I've talked about predictions from inside the wall to outside, and from the outer region to the inner region. Now, another application that I think is pretty interesting is autoencoders. Autoencoders to develop nonlinear modal decomposition frameworks. And this is a work that we have published also this year. So this is Abasi and others. You can find it in Expert Systems with Applications. This is a very nice applied machine learning journal. So what we use is different types of autoencoders to, in a way, try to outperform what we can do with POD or PCA. No? POD or PCA, we obtain linear modal decompositions, but with autoencoders, you can do it non-linearly. No? An autoencoder is going to set in the latent space a compressed version of the input data. Now, the point is we want hierarchical autoencoders, so that in a way, what we can do is that we can find ranked modes. So the autoencoder modes that we obtain are ranked from more to less energy. And what we can also do is use this architecture, the beta variation autoencoder, which allows us to perturb the information in the latent space. And we do it in such a way that we can impose a constraint. And the constraint here is the orthogonality. We want these modes to also be orthogonal, because orthogonality is a very important property for interpretability and for efficient reduced order modeling of complex fluid flows. So what we show here is for two different hierarchical and non-hierarchical architectures, how the modes are not orthogonal. And in this matrix, I have modes from 1 to 5. The POD, of course, has 100% of orthogonality, because by design it's orthogonal. But the beta variational autoencoder has over 99% of orthogonality. So the modes are actually very orthogonal, which means that a particular physical phenomenon is mapped only on one single mode. There is not any entanglement among the modes. What we can see is that our nonlinear hierarchical and orthogonal modes can be used to build reduced-order models. This is a turbulent flow case. So these are actually two buildings, and this is a DNNs database. This is the reference of an instantaneous snapshot. And what we can see is that with 5 POD modes, we can only reconstruct 32% of the energy, which is very, very little. If we look at the various autoencoder approaches, we get around 90%. The beta variation autoencoder gets 87% of the energy. So with only 5 modes, I reconstruct most of the energy in a setup, in a framework that is orthogonal and that is very, very compact. So with very few autoencoder modes, I can actually reconstruct most of the energy, which is something pretty promising in the context of developing ROMs, reduced-order models for complex turbulent flows. This has been shown, by the way, for the first time here in turbulent flows. It has been shown for cylinders and things like that, but this is really the first time that we use autoencoders who are also orthogonal for nonlinear modal decomposition in real turbulent flows. And now we have another application, which I mentioned at the beginning, which is that of pins, physics-informed neural networks. You can see the article in arXiv. This is also a Vasi and others, 2021, where what we do is that we're going to consider the Rans equations, the 2D Rans equations, steady. And what we're going to do is to use the framework of pins for solving, for minimizing the residual of these Rans equations. And the key is that I'm not going to assume any model for the Reynolds stresses. So I'm going to solve the Reynolds stresses as part of the covariant equations. Okay. So what I have is boundary data, which I can see here, and this is required information. And I'm going to solve the covariant equation. I'm going to minimize the residual of the covariant equation in these collocation points that we have inside the domain. And essentially the loss has two parts, right? One part of the loss is to minimize the residual of the Rans equations, and the other part of the loss is to be able to match at the boundaries the boundary conditions. No? So we want to be able to converge to those boundary values. So the output of my network is going to be the mean flow, including the pressure and also the Reynolds stresses. So we are not assuming a model for Reynolds stresses. We are actually solving them as part of the covariant equation. And now you might ask, so why do we use pins to solve the covariant equations and not any numerical method that is already established? The point is that pins have an advantage in certain cases because they exploit what is called automatic differentiation. So I'm learning a function that is approximating my solution, and that function can be differentiated analytically in these collocation points. So in principle, I have a mesh. I can get away with a mesh that is much coarser than that of a typical Rans simulation. So we compare this with a Rans approach. The computational cost is very similar, but we have the advantage of predicting very well the Reynolds stresses as opposed to what happens in traditional Rans. So the first case, which was taken as a sanity check, was the Fallner scan boundary layer, which is a laminar solution, a pressure gradient boundary layer in laminar conditions. And of course, we could predict the flow with less than 0.1% error. So pins can perform well in these cases, which are trivial. If we take a zero pressure gradient turbulent boundary layer, which goes up to a Reynolds theta of 7,000, so this starts to be a more challenging flow case, what we can actually see is that pins can predict very well the mean flow and the Reynolds shear stresses, and even the boundary layer development, no? Shown here in terms of the shape factor and also the skin friction coefficient. So we have 1% error in the mean, and the Reynolds shear stress has 6% error, which is quite reasonable and probably much better than you would get with a typical Rans simulation, no? An industrial Rans simulation. We can also do something similar for pressure gradient boundary layers with constant pressure gradient. So this is a very nice database that you can find in Bobke and others in JFM. And what we do is that we keep the pressure gradient parameter beta equal to 1. Okay? So this is a more challenging flow case. we get 0.28% error in the mean. You can see that we again predict very well the mean flow and the fluctuations, also the boundary layer development, and we get 8% error in the Reynolds shear stress, which again is actually quite good in this type of framework that we can define here. More things. We also looked at turbulent wings. So this is actually a very nice database where we did well-resolved large-scale simulation, so essentially very almost DNS resolution of turbulent wings up to a Reynolds number of 1 million, which is a quite high Reynolds number. You can find the database in Vinuesa and others in this article in the International Journal of Heat and Fluid Flow. And we pick one case with Reynolds number of 200,000. So this is a turbulent wing. This is a quite challenging case where we can actually get some insight for the turbulence statistics that we're going to get. And what we show is that, again, the mean flow and the Reynolds stresses, including the outer region, the outer peak of the streamwise velocity fluctuations, which are very challenging to predict, we can actually get them quite well. We can get a prediction of the outer peak and the distribution of energy between the Reynolds shear stress and the wall normal velocity fluctuations, with a mean error of 1.5% and Reynolds stresses that are still very, very well predicted. So even in these complex flow cases, we actually get very good predictions with pins. Again, much better than you would be able to get with industrial runs. And here what we have is an application to a periodic hill. Periodic hill is this flow case that you see here, which is very widely used for testing trans models, basically, and LES models, and is characterized by having a large recirculation bubble. No? So in this case, it's actually quite amazing that PINS is able to predict extremely well the recirculation, the size of the bubble, the reattachment point, and the magnitude of the recirculation. So we can actually get a very good prediction also in this challenging case with mean separation. This is one of the challenges of RANS models. And here we get less than 3% error in the mean and still reasonable predictions of the Reynolds stresses, again, in a case that is very, very challenging involving mean separation. Okay. So after talking about pins and how we can exploit these neural network frameworks to solve covariant equations, the last part that I wanted to mention today has to do with flow control, no? Because I mentioned in the title modeling, predictions, and also control, no, of turbulent flows. In this case, we start with a case that is a bit simpler than a turbulent flow, but we're actually using the same methodology also in turbulent channels as we speak. So we're going to use what is called deep reinforcement learning, DRL, where we will have an agent that you can see here, which interacts with an environment. And the environment is the flow simulation, and the interaction is through actions. So certain actions are done by the agent on the environment. The environment changes its state. So this is the state. And that action has a certain reward associated with it. And the reward is just a measure under some norm of the quality of the actions. So we want the agent. And this is, by the way, what the AlphaGo 0 was doing through reinforcement learning. It was trying different things and progressively learning. This is what the control that we want to devise here is going to do. So we develop an algorithm that through interaction with the environment based on its state is going to get a certain reward. And the goal of the reinforcement learning is to define a policy pi such that we obtain a certain set of actions given the state of the environment, in this case of the flow simulation, so that we can maximize the reward. This was presented last year in the APS, so in the Division of Fluid Dynamics of the American Physical Society. So this is a quite big meeting, and we are now developing several papers on it. So what we are showing is that we want to reduce the recirculation bubble in this very simple 2D channel. This is a first case. It's a 2D channel. What we do is that we impose a boundary condition at the top through suction and blowing. So we create a separation bubble, and we have a control region where we're going to actuate in order to minimize the length of this separation bubble. This is a case to assess the feasibility of this method. And what you see is the case setup over here. So in this channel, the color region is the one with negative velocity. So you can see here the recirculation bubble. The orange dots are the probes where we can observe the flow. This square here is the control region. So we're going to set the actuation at this point. And this blue arrow denotes the reward. What we want to do is reduce the separation bubble so we can actually basically minimize the length of this detached region. No? And this, in the case of turbulent wings, of course, separation wants to be minimized as well, because this is an aspect very important for flow control. So this is one of the areas where flow control can actually help us and succeed. And these are the results. What you can see on the left is a video of the type of control that the deep reinforcement learning is setting. What you will see is that we have basically two frequencies. No, one frequency that is associated with this short lengths, these wave packets that are being sent. So the basically this DRL, this reinforcement learning, is setting wave packets. And there is another frequency associated with the length of the bubble, with the time scale of the bubble. So it's sending pulses of these wave packets, which are very narrowly spaced in time. And between those pulses, there is some characteristic time associated with the length of the bubble. For this case, we compare the reduction of this separation bubble. This is a very small actuation, by the way. And what we see is that the DRL leads to around 30% bubble reduction, whereas the classical solution based on periodic forcing also leads to only 20% of the separation length reduction. So in principle, we have quite some potential here to apply this with more challenging cases, more difficult scenarios with turbulence where we are actually deploying it, and also to tackle separation in large aerodynamic devices. So this is a very promising area. And the idea is that the deep reinforcement learning will be able to develop control strategies beyond what is already known. So control strategies that are more sophisticated and that are unexpected compared to the classical approaches that one can find in more traditional scenarios. No? And this is a summary of my presentation. I talk about CNNs for non-intrusive sensing. So we actually can get very, very good predictions very close to the wall. We also use GANs for super resolution applications in turbulence. We use autoencoders for nonlinear modal decompositions and building reduced order models. We employ pins for runs, not exactly runs modeling, but more for solving the runs equations in certain cases. And we also show the feasibility of deep reinforcement learning for flow control, which is a very, very promising application. So this is my contact information. You can see my email, the web of my group, and also my social media. So in case you have any questions, you can get back to me later on, and I can be in touch and we can discuss if you're interested. And at this moment, I'm very happy to take your questions that you have after my seminar. Thank you for your attention.